It's just it's inconsistent. So maybe I don't need to get rid of that one. Maybe I just need to throw in a few more guided examples throughout my notes. So, yeah, so we're going to learn about concavity and points of inflection. So concavity is function as a hill or a valley. So it's concave down if it has a hill, it's concave up if it has a valley. Points of inflection are any locations in which you're changing in concavity. So if you're going from down to up or up to down, that transition point is the point of inflection. Oh no, it broke my thing. Oh wait, no, it's just unscrewed a little. All right. So I'm going to draw a little diagram here. Nice sweeping diagram there. So this diagram has both types of concavity on the first interval. No, I was fixing the color palette. I was gonna say it's not. I didn't have a green of this variety, so I needed to. Okay, that's the best I can do. So this is concave up. Oh, I don't need that so thick anymore. That's outrageous. Oh. Concave down. And then this guy right here is we call it a POI. All right, so point of inflection. So part where it's facing upwards, so it's bowed in such a way that, if it was actually a physical object, this is how I learned it. If it were a physical object or a landscape or something like that, this part of it would hold water, so the water would pool up in the area, the relevant area, and then this one would have runoff. It would spill water. All right, so, and the abbreviation is cup, and cups hold water, and then there you go. All right, so. I don't have a fun abbreviation other than to say it's not concave up, so CD. But if you understand the concept of concave up, then concave down is the other one. And so you're in pretty good shape. The point of inflection is the transition point between the two types of concavity. Exactly at the location I indicated, I don't know because I don't know what this function is, but it's somewhere in that neighborhood. All right? And so our job is going to be to determine on a graph whether it's concave down or up, or where it's concave down or up, and any transition points between concavities, so points of inflection. All right, the process is pretty straightforward. You're going to find the critical points, so that's steps 1 and 2. That'll go in your sign chart, but then you're also going to find the second derivative. When you set that equal to 0 and solve, that could give you a point of inflection, possible point of inflection, not necessarily, right? We put it in the sign chart to flesh out whether or not it actually is. Because if there is a change in concavity around the point of the suspected point of inflection, then that confirms it as a point of inflection. But if there's no change in concavity, then it's not a point of inflection, right? So it's possible that you could have a critical value of, let's say, 2. And you also set your second derivative equal to 0 and solve that and get 2 again. And it'll turn out that 2, it could be a relative extremum or a point of inflection, or maybe it's neither. All right, so it might just be a number that has a derivative and second derivative, or for the graph anyway, the function has derivative and second derivative equals 0 at that number, but it's neither a point of inflection nor a relative extremum. All right, so that's why we create the sign chart to flesh out all that stuff. right? So the guided example, I did all that. I think it's a pretty decent guided example. And it's polynomial. If we did it together, it would be probably a little on the easy side. So we'll do a harder one again. Yeah, I think I like the guided example here. So I just need more throughout my notes. All right, so my derivative, set it equal to 0, solve, we get these numbers. Second derivative, set it equal to 0, solve, I get that number. These numbers, the first two values, those are our critical values. I didn't set it equal to 1 over 0 because it wasn't relevant. So these are my critical values, and this is my possible point of inflection. All right, so then I create a sign chart containing the critical values, the possible point of inflection, any discontinuities, if they exist. I mean, it's a cubic function, so it's everywhere continuous and differentiable. All right, so starting at negative infinity, going to positive infinity, I stop at the lowest value, which is negative 1. Then I go from the lowest to the second lowest, which is negative 1/2. Then I go from the negative 1/2 to 0, and then 0 on. Taking note of what the signs of the first and second derivative are at those locations. All right, I just put in I put in a row of test values here so that you could have a sense of what I plugged in, either in my head or in the calculator. For this one, you may end up going to the calculator, but if you think about it, in some cases, it's really not that necessary because you're looking at something that's linear here. So making a determination of where it's positive or negative isn't really that difficult. And quadratic, same idea. But anyway, you get a positive first derivative on the first interval, so that means it's increasing, all right? The second derivative, when I plug in negative 2 in, I get a negative number, so it's concave down, all right? Then in the second interval, they're both negative, so decreasing and concave down, so there's no change in concavity, but there is a change in whether it's increasing or decreasing. So a function is concave down, but it's going from increasing to decreasing. So at that transition point, it must be a max, right? It must be a relative maximum. And if you visualize it, you know, it's a downward facing part of the graph. It's really like that chunk of graph is a parabola, basically. You know, it takes on the role of a parabola. And so all the characteristics that follow that would make sense here. Also, this confirms or supports the second derivative test for Extrema. I am unsuccessful here. All right, so we have the sign of the second derivative at the critical value is negative. That corresponds to relative max. That's what we talked about on Friday. So if we hop over to the other critical value of 0, the second derivative at 0. So plug in a 0 to the second derivative, you get a positive number. That corresponds with a relative min. All right, so the second derivative test for Extrema is at work here. Just kind of hidden in the process. But really, the main reason why we're here is for this guy. At negative 1/2, that's where the second derivative is equal to 0. I put an x for the first derivative because it wasn't really relevant. I mean, I could find the sign of the first derivative and make a determination of whether it's increasing or decreasing. But it seems that since it's decreasing before you get to this transition point, and after that it's probably decreasing through that point because it is continuous. So it just didn't seem necessary, so I just X'd it out. But anyway, at 0, to the left and to the right, the second derivative it goes from negative to positive. All right, so if I plug in a value smaller than negative 1/2, like negative 1, I get a negative number. Something bigger, I get a positive number. So it goes from concave down to concave up. That's what makes it a point of inflection. All right, not because the second derivative is equal to 0, but because we're changing in concavity between down and up. All right, so that gives us the point of inflection. That confirms it. All right, so two things need to happen. Your second derivative has to be equal to 0. That gives you the possibilities. And then after that, there needs to be a change in concavity around it. Very, very important that those two things go hand in hand, because I've had people claim that there was a I just kind of gave it away. They would claim that there was a point of inflection when there was no graph there, and it turned out it was because there was a vertical asymptote. All right, so let me just give you a quick sketch of that. So, and I might be stealing my own thunder here, because it might be in one of the next examples. All right, so there's a graph that, you know, I'd like to say is clearly concave up, but maybe not yet. We're just learning about it. But down the line, you'll agree that that's clearly concave up. But you might look at it and say, well, it's going to spill water. It's going to spill it this way. Yeah, the analogy isn't 100%. It's just generally would it hold water. Oh, okay, so well, it's concave up because it's going to hold a heck of a lot more water than this one. All right, so that's my concave down. All right, so if it's bowed, so it's taking on a parabolic form, but in the upward direction. It doesn't have to be a perfect parabola, but if it's kind of feeling parabolic upward, then it's concave up in the downward direction down. Right? But we have a vertical asymptote here at 0. I mean, I didn't give you the function, but that's my, you just take my word for it. That's basically what I'm saying here. All right, so vertical asymptote at x equals 0. All right, so there is no point of inflection at x equals 0 because of discontinuity even though there is a change in concavity. All right, very important concept. I just don't want to have to take off points on a test anymore for this. That's why I'm really kind of emphasizing it. Like every year. I mean, I would mention it in passing. I would even go over an example where this ended up being the outcome. But I really want to draw attention to this concept as its own standalone example. So I'll even take this as a typo. Like include side example on page 84. All right, that's what I'll take. Anyway, but the idea is that in, like, let's say, 19th year teaching. So this course I've been teaching for at least a decade, and every year there's like at least half of the class losing credit because they're calling x equals 0 a point of inflection, right? Because what they do is they take the first derivative, get their critical values. You know, very procedural. First derivative, critical value. Second derivative, possible point of inflection. And they'll get x equals 0 even though the denominator of the original function was x, so x can't be equal to 0. They'll put it in the sign chart, and they'll see a change in concavity around it. Never once evaluating the original function for x equals 0 to identify that it is a point of discontinuity, because if it's discontinuous, it's not differentiable. So they see a change in concavity, and just rote procedural-minded individuals will just write, oh, change in concavity. He said it in class. I wrote it on my note card. That means that we're looking at a point of inflection. How could it be a point of inflection if there is no point? Right? Yes. All right, so I am getting on your case for something that you have not done yet because of the students over the last decade plus. All right, so the sins of your forebears, ancestors, you're paying the price. Ancestors, yeah. So I'm looking 20 years into the future, seeing what went wrong. Okay, so I hit next page. Yep. No, phone not ringing? Oh, okay. So, it looks like we have a function that will be continuous everywhere. We have a sum of really two guaranteed positive values. X squared is positive, 3 is positive. So you're never getting to a 0 on that. So there's no discontinuity in this graph. But we always want to check, at least in our minds. All right, so we can go to our derivative process. Let's rewrite it. You don't have to do it this way. I'm just opting to do it this way. The quotient rule works really nicely for this because of the constant on the top.
Should we write C and D?
Generally, yeah.
Just write C and D everywhere.
Yeah, just go through the rest of your packet and write C and D.
Except when it's not.
Except for when it's not, of course, yeah. You only really have to worry about it when it's not. So, well, I mean, in terms of verifying it. So if there's a point of discontinuity, you need to flesh out where that is. If it's continuous and differentiable everywhere, if you make that statement for me anyway, that's all I need.
If I can't do first and sign, is it okay if I do C plus D?
I mean, I'll accept it, but of course I'm judging you for your inability to do an ampersand. Yeah.
All right, that's fine.
Yeah.
I like the plus sign.
I mean, if you can get over that, like.
Can't do the and sign.
They're hard.
All right, start on the right.
You can't draw one of those?
Go back, loop it over and under, and then out. The key is in this area over here.
Yeah, I don't
That little
I don't like
transition.
it's like heavy.
You got to take the turn wide, right? So that's really how.
I used to do that in elementary school and I thought it was really cool.
And you were, and you, for the record, you still are, for the ability to do it. Every time I do it, I feel just awesome.
Write it like the G cup symbol?
No.
I made it a little too round at the bottom, but it's still allowable.
No, I always do this. I use it.
It's like
You see, it has a lot of qualities of an 8. So if you're thinking 8 backwards, and then finish it up with a G,
it's like the G cup.
then you're pretty good.
I'll use it all the time.
Go back at the bird.
I do. I mean, if I go quickly, like it comes out like this. So, I mean, it's clear I was not going for an 8 followed by a G here, but it got the job done. The one caution is you will lose your ability to make an uppercase script S
Why?
because of the whole brain thing.
Yeah, but the uppercase
They're like
script S is not that
backwards.
great.
Yeah, it's not really that
It's
necessary.
kind of a D.
Because it's really just, it's very similar of a process, just in the reverse.
In script, like, doesn't look like it anyway. So.
Yeah, so.
Yeah, so just toss it anyhow.
It's not a big ball.
Alright, so derivative.
I'll just like write it.
I suppose we should probably do that or something.
When we go, it's
So F prime.
Someone sounds jealous that they're not in a real life.
I usually do an ampersand tutorial way earlier in the course, so the fact that we got this far.
This is about to get really complicated.
AP Calc, learning the things that matter.
Exactamundo. Learn how to make chili. Actually, I never really went over that.
I never learned.
Never really. We didn't really get into it. You just learned how it could be delicious.
My mom made lasagna last night.
Learn something. It could be.
Yeah. But again, I don't think many people got the full effect because you all missed the bag of shredded Mexican cheese blend
Oh my bad.
that was right next to
No, I
it.
saw it.
I mean, I don't.
Oh, what?
Or you just opted out, yeah.
I'm also
It was right there.
I have an idea, and I think we should go along with it. So, like, for the rest of the year, once a month we should have like a food day where we bring food.
I'm not too well.
I mean, there's merit to that idea. Yeah.
And watch Star Wars.
And then watch that.
That'd be a strike.
Except the worst case for chili part.
So what that? Yeah, 2 weeks. So back
Table the conversation for 2 weeks. And
No, last kid is
I have extra credit.
So what?
I'm pretty sure I'm not allowed to do that unless it involves calculus in some way. I'm sure we can come up with a plan.
I'll totally do that.
You could calculate which board is the most sittiest.
How would
The
you
most
calculate that?
I think it would have to be Bane, Darth Bane. I mean, he created a rule of 2.
I'm concerned that if your belly's eating that much.
What do you define as like
I mean, you got to be very sithy.
What are we doing?
No, I know.
It transitioned into Star Wars stuff.
What specifically defines sitting?
All right, so for my critical values,
No.
I know, acceleration.
Sorry?
I like to acceleration. Constant acceleration of acceleration. You have snap.
all right. Well, anyway, so that sounded like fun, but I guess we have to do this.
Oh, right. Oh my God, you're so right.
So for the critical values, you want to set the top equal to 0. Well, you're really setting your derivative equal to 0, but that's equivalent to setting just the numerator equal to 0. And you also want to set it equal to 1 over 0, which is equivalent to setting the denominator equal to 0. But because we've already talked about how x squared plus 3 is never going to get you 0, why would x squared plus 3 quantity squared give you a 0? So nothing here, but we do have a critical value of x equals 0. All right, so that's the first part and the unfortunately easy part. We then need the second derivative. So we need the derivative of this guy. So, quotient rule, a little baby chain rule mixed in there, nothing too crazy. So low D high, so that's going to be negative 12 x squared plus 3 squared minus the high, so minus negative 12x, so plus 12x. D low, so that's going to be the little baby chain rule there. So it's adorable. Over the denominator squared, and where we go, all that good stuff. So, barring any mistakes, entirely possible, I suppose. But we do want to simplify this, not because I'm telling you to simplify it, but because it's, we have to solve by setting equal to 0. So, I mean, I suppose you could get it done just by setting equal to 0 and going after it like an animal, but you probably want to clean it up a little bit more first. I mean, just the thought. And cleaning it up doesn't involve, that's the good news, it will never involve expanding out the denominator. So that's important to realize, because I see that a lot, like this monstrous expression on the bottom, like, well, okay, so that cost you like 15 minutes and you didn't need to do it. And in fact, it worked against you. So don't do that. Also, distributing out the top may work against you, because I notice here that we have a common x squared plus 3 that can be factored out and canceled across the board. So let's do that. And anything else that could be pulled out, you want to pull it out, right? So, I mean, there's really not much left. I suppose I could pull out a 12. Is that going to advance the cause? I don't know. So at this point, you can go either way. But this part is much nicer, and this part, it really doesn't require any effort. If we're going to simplify now, it's probably going to happen through addition and subtraction. So we can distribute on the top only. Negative 12x squared minus 36. And then we'll have, really, it's just multiplying these three things. So 12, 24, 48x squared, so plus. Now, in the second derivative, so the second derivative test for concavity, we're not setting the second derivative equal to 0 and 1 over 0. It's just equal to 0. So that denominator is very quickly going to become irrelevant. Simplify the top even more. 36x squared minus 36 over x squared plus 3 cubed. You leave it like that if you want. That would be our second derivative. You can factor it more if you want, but you don't unless you have a reason to, right? So we'll see if we have a reason to later on. But we do have to set it equal to 0. Which is the same as setting the top equal to 0. I can kill the 36's. So our solution would be x equals plus or minus 1. Now, just bear in mind, so we tend to write it as plus or minus 1 for simplicity. You may see the absolute value of 1 as a solution also. All right, you could write it either way. This, I think, the plus or minus 1 is more meaningful, but sometimes they'll put critical value x equals absolute value of 1 as a multiple choice solution. So we want to be prepared for that also. All right. And you'll be like, well, that's clearly not it, and it ends up being the right answer.
But that is a negative 1. Like, I know that if you put negative 1 in an absolute value sign, it would be 1, but you're not giving the person that chance to make it negative 1.
Right, but the absolute allows it to be positive or negative. Yeah.
Okay.
You're not giving it an opportunity. It wants to be negative, but you're not letting it. I understand that. That's a fair point.
Justice for negative.
So now that we have all this stuff, and again, we're going to go with this one. This is my possible point of inflection. Pos-poi. We have 0 and plus or minus 1 as my important points in my sign chart, the one that they don't tell you that you need to make, but you need to know that you need to make. So x, negative infinity to negative 1, negative 1, negative 1 to 0, 0, 0 to 1, 1, and then 1 on to infinity. So we need f prime, f double prime, and conclusion. And then I need to attempt to draw lines. Yeah. Okay. Kinda. Whatever. See, the line draw tool is letting me down here. Sufficient. Oh, that hurts so much. All right, so we need to work off of our first and second derivatives here, and there's no assumption allowed that you're able to use a calculator even for a question like this, right? So you have to assume that even the complicated ones, you could be expected to do it without a calculator, all right? So that's a very sobering thought. Anyway, the good news is, if I look at my first derivative, I can get all my signs in one shot, right? Second derivative, we need a little bit more effort, but the denominator has to be positive all the time, right? Because it's a quantity squared, so it's irrelevant. The numerator is going to drive the quality of our derivative, because if x is a negative number, the derivative is going to be a positive result, because it's negative times positive. If the derivative is positive, if x is positive, then the derivative will be negative, right? So we can go right across the board now and get all of those. So negative x gives us positive first derivative and vice versa. But it's those little relationships that you need to be able to identify, right? Because otherwise you're actually plugging in numbers. You're plugging in a -2. What does that give me? You plug it in the top and the bottom. You know, sometimes you got to plug in a fraction, and it's not fun. If you can avoid doing that, it's obviously a time saver, because I just got through 4 calculations without doing any calculations, right? Any real calculations anyway. So then we have the second derivative. The bottom also still going to be positive, even though it's raised to the 3rd power. That's fine. The quantity contained, x squared plus 3, is always going to be positive, and positive cubed is positive. So denominator irrelevant. Now I just got to worry about the top. All right. So we want to think about what's going to happen here, and you can do it if you want. A good intermediate step would be to come up with the factors. So that's the same as 36 times x squared minus 1, but that goes to x plus 1, x minus 1. All right. The reason I'm doing that, it's coming. Yeah, there it is. The reason I'm doing that is to really emphasize the idea that you can come up with these values without having to do the rote calculation, or at least oftentimes without having to do the rote calculation. All right. Just by thinking of the quality of the numbers. So the 36 is now irrelevant. That's the important piece. The part that was making the top hard is irrelevant because it's positive. All right, so I would want to think about what's happening in these factors here. So if I have a number less than -1, that's going to make this negative and this negative, right? So then negative times negative would be positive. If I have something in between -1 and 0, right? So like -0.5, positive, negative. So result would be negative. Between 0 and 1, so like 0.5, positive, negative, so still negative. And then something bigger than 1, everything's going to be positive, right? So you can confirm by putting simple numbers in. But again, you'd rather put the simple numbers into a simpler part of the expression, right? So you still have to draw the conclusion that the bottom's irrelevant, the 36 is irrelevant, and the only thing that's going to drive the type of number would be these 2 factors. All right, so if I put in a 2, both parts are going to be positive, and the overall result will be positive. All right. So conclusions: increasing, concave up, increasing, concave down. All right, changing concavity. That makes this a point of inflection. All right, didn't ask for it, but why not, right? For practice anyway, on a test. If it doesn't ask, don't tell me, because if you screw it up, I'm taking off. So concave down. All right, so here we have a change not in concavity, but we have a change between, change in slope, so increasing to decreasing. So it's going uphill followed by downhill, so it must be a relative max. Then we have decreasing. Saw that plus sign right in front of me and I just went for it. Decreasing and concave up. So again, change in concavity makes it a point of inflection. All right. Now, it doesn't ask us to do it here, but eventually we're going to get to a point where we'll have to come up with a sketch, but now we have a lot of information to help us come up with a sketch of the graph of the original function. Because I know that it's increasing, then decreasing, right, overall. And then we have 2 points of inflection. So maybe we're looking at something like kind of like a normal curve. It's continuous everywhere, the original function. Right? It goes from, it's increasing to decreasing, so increasing to decreasing. We have concave up, down, up. It could look something like this. All right? And that would be all I would need from you. Nothing on a graph, no scale, no axes labeled, no points plotted or anything like that. draw a sketch of what you think this function would look like based off of the given sign chart. All right. So sometimes I'll even give you the sign chart, all right, or at least elements from the sign chart, and you can come up with the graph. But this is kind of the gateway to getting us to that moment. All right. All right. So, oh, look at that. Good looking solution. So why don't you try number 2 for homework? It's a good looking problem. All right, I set up the domain so that you don't have to worry about discontinuity in your original function, because tangent is undefined at negative pi over 2 and pi over 2. But the parentheses are telling us that we're excluding those values. So the discontinuity would be irrelevant. So it may be a little bit easier than it's easier than it seems initially. I mean, it's still going to be work, but not insane work that it might seem initially.